titled it, "Wow, CT is here, revealing ancient secrets in the digital research lab." Yeah, we really like the notes in the Egypt exhibit. They're very funny. I'm Eldon Panigot. I am one of the 2 techs in the digital research lab right now, and I'll let my friend introduce herself.
Hi, everyone. I'm Lindsay Dougan. I work in the digital research lab with Eldon, and we are going to go into an overview of what we do in our lab. I wanted to point out there are a couple of images in this slideshow that have this QR code. If you get out your phone and scan that code, it will load the models that are showing up there so you can actually interact with them on your phone. There's a couple in there. We have a lot more if y'all are interested in seeing other ones. But otherwise, let's go. Yeah, this is the mummy, one of the mummies from the exhibit upstairs, which is also tied to our WOW CTs here.
Yeah, you want to actually look at the scan because I don't know how to do it.
Yeah.
Thanks.
All right. So this is a scroll through the CT stack. This is what it looks like when we get the data, and then we turn it into something 3D and awesome. But right here, we're moving through the skeleton, so that really bright stuff that you see, those are all skeletal remains. Everything else is a soft tissue or soft material like linen fibers and things like that. And in this program, you can go back and forth between the 2D and the 3D, so you can see both versions of what we work with in our lab.
So a little bit about us to start with. Obviously, me and Lindsay are the paid employees that are, we go to department meetings. But we also have a lot of interns and volunteers that we couldn't do all this work without. So thank you to Brianna Yappy, Mariah Figueroa, and our intern Joel Crothers, as well as our volunteers, Greg M., John H., Greg T., and Sophia C. Our involvement in science division is mostly project-based in earth sciences. So right now, we're on the Colorado Springs project. We work with a lot of the Corral Bluff stuff that you'd see in After the Asteroid. And I am specifically funded by the Origins of Turtles and Diapsids grant by NSF. So I work with a lot of ancient Permian reptiles and potential turtle relatives and whatnot. We also have lent our assistance to Jurassic Giants. We've 3D printed a couple things, given a little mild tech support to that one. And we're going to be doing that pretty soon with Teen Rex as well. And the lab actually started with the Madagascar project. So when was that? 2017? Yeah. Lindsay was hired to start processing some of the CT data from that. So what is CT data or computed tomography data? It's fancy x-rays, as the slide says. So imagine taking any object, in this case fossils, and slicing it as if it were a loaf of bread, chopping it up, and taking out a slice, and you'd see the rock matrix, and you'd see cross-sections of all the fossils, and the cross-sections are what we're really interested in. But unlike slicing up bread, the CT data is non-invasive, it's non-destructive. The fossil looks the same before as it did after. And with this technology, we can see inside of a fossil and get details that are never going to be visible to the naked eye, at least not without breaking something. Do we have a scanner? No, unfortunately we don't. We actually send our fossils to a lot of other places to get scanned. So we get the benefits of a lot of institutions, such as University of Texas Austin, American Museum of Natural History, Lockheed Martin in Littleton, North Star Imaging, and Wheat Ridge Veterinary Hospital and the Children's Hospital. So yeah, our stuff goes everywhere. Honestly, just depending on what we might need at the moment, a fossil might literally be too big for a certain scanner, or certain people might have certain expertise that we need for a specific specimen. And why do we do this? Why do we care? Well, first, we have to take those... The screen went black. Sorry. Odd. Wow, CT is here. So we start with those sliced bread cross sections I mentioned earlier, and we take those cross sections of fossils and paint them, like trace them out, almost like you would in MS Paint. And we do that for all the bread slices or all the CT data slices. And eventually, 100, 200, 1,000 slices later, you get a really nice 3D model of a bone. Or you can get something that isn't bone. You can get the model of something inside of bone. So that can be a brain case or something. And our main goal with this is to just create a model of a fossil or see something that you, like I said, wouldn't be able to see normally. But there's a lot of side effects. We can share models like almost limitlessly. And when I say limitlessly, I mean we can 3D print them as many times as we have the money for, or send them across the world to anyone who has a computer. We can grow and shrink them, so some fossils are the size of like my thumbnail and very hard to decipher important anatomy details from, and that's an easy problem to fix. We just take a corner and drag it in a program, and it gets a lot bigger. We can reconstruct fossils, so if something's just broken to pieces and shattered, we can literally put it back together in 3D programs. And with some of the 3D prints we make, we can preserve in situ positions of fossils. So sometimes when we have like a big fossil bone bed, graveyard, whatever, we can, prep will sometimes disturb those positions, even though it needs to be done. And if we have the CT scans and the 3D models of all the important objects, that gets preserved in space. So even though we're moving things, the relationship in space can still be preserved. And we can allow guests to touch the fossils without putting them in danger. So after the presentation, we have a bunch of 3D prints up here, and you guys can come up and play with them, inspect them, whatever. And now I'll hand it off to Lindsay.
All right, so most of the stuff that we do in our lab are fossil-based. Lots of paleo, mostly vert paleo. Occasionally we get to look at some invertebrate stuff. But because we're looking for bones, we typically want to work with vertebrate fossils. And they usually come in 3 different types of preparation levels when we scan them. Some of them are fully prepped. Those are our favorites because there's not a lot of matrix hiding any of the fossil bone. Some of them are partially prepped, so it's usually a surface prep where one side is still encased in matrix, but the top side has been exposed. And then we also do scans of things that are actually still in field jackets, so they haven't even been opened since they were collected in the field. All of these present very different challenges and different results, and you'll see why prepared fossils are our favorite ones to work on. The unprepared specimens that get scanned in field jackets are the most difficult to prepare. As you can see over here, there's a lot of stuff around the fossils. So it can be the plaster jackets, all of the material in there to keep the fossil safe, all of the rock matrix, and the fossil is deep inside of a lot of this stuff. And a lot of times, for some of these fossils that we have, the matrix, the rock that's around the fossil, has the same density value as the bone that we're trying to identify. So separating those out when the matrix is still present is really challenging. We can do it, but it takes way more time to process these scans than the ones that have far less matrix on them. The middle level difficulty are the half-prepped scans. So these are really nice because at least one surface is exposed, so we get a really nice air-bone boundary that shows us exactly what the bone should look like. If it's a really great scan of a really great specimen, we can really see the difference between the matrix and the bone. And a lot of the specimens we get typically come this way. So sometimes they are too fragile to be prepped further, and that's why we're doing the digital prep, because it's non-invasive and non-destructive, so we can get in there and uncover all the stuff that's not visible when we look at the fossil in the collections. And typically, these are really fun because a lot of times we discover that there's more stuff in there than we actually anticipated. So there's usually lots of surprises in these kinds of fossils. This is an example of a partially prepped specimen. So right here in this video, everything that's in a bright color is a fossil element, and this dark gray shadow is the matrix that was around all of these fossils. So this is a replica of everything that we've uncovered inside of this block. The block is not that big. It's maybe 6 inches long. And there's about 100 elements in here. This was work that was completed by our volunteer, John, who's sitting right here in the front. Yeah, this was a really, really great project. So many elements that you can see in there, lots of long bones and vertebrae of all kinds of animals too. So we're in the next phase of this where we're actually sorting out what all of these bones are. But the first part, the segmentation, is the most time-consuming component of this, especially when there's rock matrix around these elements. So the last ones, our favorite ones, are fully prepped specimens. This image over here on the right is actually 2 jaw elements from a new species of Tyrannosauroid that is yet to be published. And they actually come from opposite sides of the face. So we reconstructed this image, and I really want to point out this was done by our first teen science scholars in 2019. So yeah, they had no experience in this. They both really love dinosaurs, and we had 6 weeks of learning anatomy, segmentation, and they cranked out these beautiful models by the end. These give us the best view of the anatomy of these specimens, both the external surface and the interior, so all of the different anatomical features that are inside of bones, things that we're really, really interested in seeing because you can only see them with CT unless you crack open a skull. These are the things that we're really excited about. And these 2 sets of scans turned out really great. You can see so much anatomy in here. The red teeth are all unerupted teeth, so they're still developing inside of these jaws. The blue teeth are erupted teeth, so we could actually see them on the surface of the bone. And the yellow is actually the really exciting thing. Those are nerve canals. So blood vessels and nerves were traveling through those spaces, innervating the teeth, and a lot of the little ends that you see kind of cut off, that's actually where nerves were exiting those bones and innervating the skin of the face. So this is a really cool way to see way more about fossils than we've really been able to see in the past. And this is my favorite fully prepped specimen right now. This is Melitocodon, a new fossil that was described and published a couple of weeks ago from Coral Bluffs. It's a very cute mammal. The skull's really tiny. I have replicas of it up here. It's about this big. Its nickname is the peanut skull, and it's a beautiful scan. I don't know if you guys can see this, but a lot of this stuff in here that looks like TV static, that's matrix. The smooth sections that you see right in here, that's all bone. So the stuff that we're really interested in is the bone. We want to isolate those elements, and we can actually look at them individually like an exploded skull model, or we can put them together and print them without all of that extra matrix that's inside those cranial spaces. This is a beautiful scan. If you look really closely, you can even see the enamel lines on the teeth, which is always really exciting. But this was a really high quality scan from the University of Texas at Austin. So we were really lucky to work on this. And our current teen science scholars are actually working on this, so we'll have lots of cool prints at Showcase on July 24th. Yeah. And this is a cute reconstruction of what it looks like. It's adorable. So this is the movie that our 2019 TSS made for their showcase, showing a lot of the features that they identified. And this also is something that they had no experience in, creating these animations in the software that we had. So we're just creating some X-ray models. We can see a lot of the anatomy that's not visible on the specimen.
So if you've been through After the Asteroid, some of you might recognize this specimen. This is EPV 48541. It's a crocodile relative from Coral Bluffs, so that's right near Colorado Springs. It's about 65 million years old, so it's right after the KPG extinction, and the gators are still looking like this. And in the red box here, this is the area that the CT scan on the right there is showing. So as we're moving through the skull, we're actually seeing some of the brain case and some of the inner ears, if I can get the laser pointer. Yeah, we might need to roll through this again. But this was the area to be looking at. And this is just an OBS video of our software I just recorded. This is what my screen looks like a lot of the day. So here we're starting with the skull, that's this area here. And then we can see the supratemporal fenestra. These are these holes here. They're actually a really important feature for diagnosing reptiles. And as we move through, we're going to get to the brain case or the endocast here. This is where the brain would sit, and a similar structure for the inner ears here. But all that from CT data of a crocodile that has been dead for literally millions of years. So what is endocasting? That is kind of what I just laid out. It's modeling the space within a skull. It's empty space, but something might have been there at one point. It's just been decayed and not preserved. Yeah, we typically use brain molds, or we're doing brain molds when we're looking for brain molds, such as the one on this Loxolophus here. We also saw the inner ears. And yeah, the organs that we're looking for can be not even a couple microns thick. So we're looking for some pretty fine detail. Do you want to play that again? Yeah. Thanks, Lindsay. Yeah, so this is what the fossil looks like, and then these are all the bones separated out. Oh, sorry about that. No, this is the brain case. We've also got some cranial nerves here and the inner ears here. Now we have all the bones separated out. So these are all the different bones of the skull, plus some vertebrae from the neck. Then the video ends. Oop. You want this back?
So this is a screen recording of my computer. When I was working on the inner ears for this specimen, which is Unitosaurus. So this is a Permian reptile as well. It's about 250 million years old. This animal is really unique because this specimen does not live at the DMNS. It actually belongs to South Africa. So it is housed in South Africa. Eldon and I are working on these specimens, and we have never seen them in person. We have only worked with CT data. And the things that we're looking at here are the inner ear structures of this early reptile, and they look really different from our mammals. So their cochlea is not the same as ours. We have long coiled ones. Theirs is relatively flat. And their semicircular canals, which are these kind of loopy things you see, are also really flat and wide. And ours tend to be really tall and gigantic because we do a lot more movement than these kind of animals did. So the things that we're looking for in this soft tissue anatomy are the shapes of these, the length of them, how much they're coiled, what their angles are to each other. And a lot of this information can tell us how this animal is interacting with its environment and other animals around it, so we can understand the frequencies that animals were able to hear, and looking at those angles of those semicircular canals can tell us different kinds of mobility patterns, so how the animal was actually orienting its head while it was moving around its environment. So it's pretty neat to see. Also, this specimen's very tiny, so these structures are pretty small as well. They'd be really hard to see, even cracking this specimen open. Using CT means that we can scale really, really large to see these really tiny structures and take measurements of them and learn all this stuff about these animals. More CT scans. These are brains. These are my favorite. I love brains so much. This one is a human brain. This one is a chimpanzee brain. We had been asked for the Becoming Jane exhibit to print some brains for touch cards and things to really show the difference between a chimp brain and a human brain, pointing out the human scan is still going. The chimp scan is very quick. Human brains are much bigger. Also, this data set is vastly detailed. This is one of the most detailed scans of a human brain ever, and it's beautiful. You can see so many structures in it. You can also see a lot of structures in the chimp brain. Another thing to point out, the chimpanzee was scanned while it was alive. This animal is still alive, so you can see a lot of the soft tissue of the skull. You can see the eyes, musculature. On this human brain, this was a donor brain, so this patient donated their body to science, and there was a huge program set up to actually capture this brain. They created a special case to put it in a CT scanner. It had to be floated in liquid. It was partially preserved in formaldehyde, and it's just beautiful. I could look at it all day. But this was one of my favorite side projects because we got to print some brains, and we usually don't get to work with soft tissue structures.
So I mentioned we could piece fossils back together that are broken. So yeah, let's play the other one. So this is Ectoconus. This skull has been on the TikTok, actually. You can see my friend and colleague Franklin Duffy explaining it. But basically, what Franklin had to do is kind of like that Loxolophus skull earlier. He had to separate out all the bones of the skull, so they're all colored differently. And then he had to actually put the jaw back in place. So we have our one jaw here, and it's both broken down the middle and out of place. So what we did is Franklin, segmented all the elements like I mentioned earlier, and then went into Blender, created our meshes from them, which we printed, and also had to play with it both in Blender and physically to get the result on the right. Okay. So it's not all about CT data in the lab. We also have done some photogrammetry modeling. So what that involves is taking tons and tons and tons and tons of pictures of any object, fossils again, and we can create a 3D model out of that. Our preferred method is definitely surface scanning those. So we have a couple of those, and that just uses structured light to do a very similar process, but it makes its model a lot faster than the photogrammetry does. And the surface scanner models are actually much higher quality. You can see a lot more detail on them. And we also 3D print, like I've been saying this whole time. The main advantage that photogrammetry has, I would like to add, is that it's really cheap. We've seen interns do good photogrammetry work on iPhones. But the surface scanners can run you tens of thousands of dollars. So we have two scanners in Earth Sciences. We have the Artex Space Spider, that's our small fine detail scanner. And we also have an Artec Leo. That one's really portable, and it can scan some really big objects, such as the sauropod vert. Here we can see Cameron scanning a pretty small skull. It looks like it's that big. It's a lemur. Thanks, Lindsay. And Evan from the prep lab, she, in that image, is scanning a whole door, actually, at History, Colorado, as well as Salvador using our Leo to scan sauropod vertebrae. That thing is huge. That thing takes up the whole cart. And we've managed to use the Space Spider to scan the rhino horn, which is what's going on in the top right. And once all is said and done, once we've done every little thing, it's been scanned, it's been processed and 3D printed. We have all kinds of fun deliverables. We've been showing you the movies this whole time. We make some really high resolution images because that's what scientific journals ask for. We still have the scan data, so that's Sahona-Keeley's is the rainbow skull, and then Lindsay's scrolling through the same CT data that we used to make all that. And we do the 3D printing. It's always really fun and really satisfying. And we can do some really big stuff. So that at the top right is a whole Neanderthal footprint at actual size. Then we have skulls at their actual size and also really big. And we can also print out all the individual elements of the same skull and piece them back together for our reconstructions that we keep doing. That's the end of the talk. Thanks for coming, guys. Yeah, big shout out to all the interns that we've had over the years and the volunteers that we've had over the years and currently have. I also started as an intern, so.
Yay. Also, a big shout out to TSS because they've done really awesome things in our lab, and it's nice to have them.
Question time.
Eldon's getting the cube.
How does the cube even work? I don't know. You squeeze it. It's on? The cube is on? It is on. All right. Any questions? Doesn't sound like it. A lot of you have basically seen this talk.
Or do you just want to come see Prince?
Hi. So I'm curious with CT scans, you're doing like a lot of the corral bluff stuff. When you have like a bunch of mumble jumbled bones from maybe different individuals, how you're able to like figure out which individual bones belong to, or what that process is like.
That is a great question. It is a very long process, and it involves wrangling curators to come sit with us and actually look at all these bones. Sometimes we print them out. If they're really challenging to see in 3D, then we actually print them so that we can have something to touch and actually manipulate. Right now, a lot of the stuff we're looking at is in that phase of reviewing what we have and assigning taxa to it. We're also looking at what bone it is, if it's a left humerus or a right ulna. When we're talking about identifying the number of individuals, we're looking for the minimum number possible. And we've actually had a lot of surprises in this department. There have been times when we thought we had 2 individuals, but it turns out we have 3 left dentaries, so that means there's 3 crocs in there. We've found a couple of fully articulated limbs that are from the same side from the upper arm, and so that tells us that there's probably multiples of those as well. It's tricky because not all the bones are complete, so there are a handful of bones that are just unknown, and they will always be unknown. But we still throw them in the count because they're still fossil elements, and they made their way into the block.
Thank you.
So you're here. All right, here you go.
I guess this depends on the size of what you're working with, but how long does it take to separate something out, process it? Yeah.
Very long time. The largest project that we've worked on is still pending. We're hoping to publish on it maybe within the next year, but it took over 5,000 hours for us to segment about 150 elements out of this massive block of rock. Yeah, there was a lot to go through. It was Eldon was working on it, I was working on it, Cameron, Franklin, and Hannah. So we had a lot of people plus additional volunteers. And I think the total was over 5,000 hours for that. It's very tedious. We have a lot of patience.
Nice, I love that throw. This is great. I have 2 questions. One is, how do you use structured light imaging? And can you use AI, or are there developing ways to use AI to do some of that work that took you hundreds and hundreds of hours?
Excellent questions. The structured light scanners are special, so they actually map what the light is reflecting back to the scanner. And they also have cameras inside, so they're taking photographs as well. It's real-time scanning, so we can actually see what is scanned while we're doing the scan. With photogrammetry, you just have to take a lot of photos and hope you got enough to make the model. But with the structured light scanner, we can actually see the model being built in real time. So we know if we got all the data or if we didn't. And that's a great tool to have. For the AI question, it is a really great question. The software that we use for segmentation is called Dragonfly, and they do have a really robust automated AI segmentation component. The main issue with us is that a lot of the data sets we work with are not as clean as the AI segmentation wizard wants it to be. So it can help by identifying where elements may be, but the actual really nice segmentation still has to be done by us because it can't fully separate the matrix from the bone that's in there.
Okay, a few questions. I'm right here, so we'll go with you, and then we'll go that way.
Thank you. You had mentioned Blender and now Dragonfly. Are there any other softwares that you find yourself using on like a daily basis?
Yes, great question. Dragonfly is our main program, but that's only because we spend most of our time doing segmentation. Blender is where we actually construct all of our animations and our figures. Depending on what those deliverables are going to be used for, we can put them into Adobe programs. So we'll use Photoshop, Illustrator, Premiere Pro to get those publication quality deliverables made. But on a regular basis, especially when we're reviewing files with our curators, we use a program called Cat Assist. It's open source, so anybody can download it, and it's actually pretty robust. We've put it through its paces, I would say. We have a couple of sessions that have about 500 elements in them, and we can actually load every individual element so they have names attached to them. We can change the colors of them so we can see them against each other. And that one actually we've been using for maybe 6 months or so, and it's been a really good help in the lab because we're actually able to load things without having to put it into the software like Dragonfly and work through something that's really robust when we just need a 3D viewer. Our software for the printer is proprietary to our printer. We have a Formlabs 3L, so we use Preform to set up all of our printers, and occasionally we use Maya. I think we're moving away from Maya because Blender is an amazing program and it's free, and we don't really want to pay for anything if we don't have to.
Yeah, our surface scanners also come with their own program, so that's called Artec.
Yes,
We use that a
Artec
lot.
Studio.
Yeah. My hand's here. Closer to you, so I'll go with you.
Have any of the scans kind of like revealed any superstitious deaths?
No, because we haven't been able to scan any cool stuff like that. I would say the coolest thing closely related to that is the mummies, but it didn't reveal anything about how they died. The thing that I found most exciting about the mummies is that even though they're thousands of years old, their anatomy is great. Their musculature is well preserved. You can see all of the muscle groups. It's just so beautiful to see, especially if you're an anatomist like me. It's really cool to see that. With the fossils that are, millions of years old, the really interesting thing about those is that the body structure is already set so many millions of years ago. So the first specimen that I saw when I started this job that really convinced me to actually do this was a scan of a forearm of a modern mammal. Well, not modern, it's technically extinct. But it was modern for me. Anyway, it was the elbow joint, and you could see all three of the bones that make up that joint. So the distal humerus, the proximal ulna, and the proximal radius. They were almost in perfect articulation, and the scan was so good, it was such high quality that you could actually see the epiphyses on all of these long bones. So it was a beautiful preserved anatomical feature. It was from a subadult, so it wasn't fully grown, skeletally immature. And it matched exactly like what a modern human elbow looks like. And it's 60 million years old, so it was pretty cool.
All right, this is kind of a question for both of you. What is your guys' favorite projects that you've worked on, and your least favorite projects, or at least the project that you guys found the most annoying to work on?
I can go. My favorite project is definitely Origins of Turtles and Diapsids, because I'm just very partial to reptiles. I love reptiles. They have teeth everywhere, even where you don't expect it. That's really fun. The most annoying ones are when the scans aren't very good, and what that means is that you just can't tell the difference between bone and surrounding rocks, so it might just look like TV static or monotone gray. Yeah, that tends to be a lot of the really big objects, unfortunately. It's just a natural limitation.
Picking my favorite is really hard because I like a lot of the things that we've worked on. I think skull scans are my favorite because cranial anatomy is so different across every kind of animal you could think of. And when we're doing endocasting is actually my favorite component of segmentation because we're getting to recreate soft tissue structures that most of the time no one has ever visualized before. So we're getting to see these anatomical features that are new to science because we've never had them before. And so that's always really exciting to me. For least favorite, probably the project I just finished because I spent thousands of hours on it and I'm just over it.
Oh, yes? Oh. You, sir? All right. Excuse me. Sorry.
Thanks. So I have a question with kind of a lead-in. I come from the human medical imaging side. So question is, what new technologies do you see, coming up in terms of scanning and maybe you already kind of touched on AI. And the lead into that is on the human medical imaging side, there's new CT technology that is spectral imaging, where you can kind of tease out different photon energies and look at those in isolation, which in living tissue, that really helps with tissue differentiation. I wonder if that might help with differentiating matrix from fossil and make the whole job a little easier.
That would be amazing. I would definitely be willing to try it. One of my mottos is like, let's just scan it and see what happens, because it's non-destructive and it's non-invasive, so it will work or it won't. And if it does, then we can usually get some really great results. What we usually work with are industrial CT scanners, so they are built at super high power, and they can scan at really, really high resolution. So our Melito codon scan was actually 22 microns per slice. So each slice went through that fine, so we have a lot of detail for it, and that's why we can see the enamel lines in the teeth. The main issue that we encounter is that sometimes the scanners just are not built for the kinds of fossils that we're trying to capture, and that usually results in blowouts, so we just get white data because everything is really dense or it has the same density. And so if there is a way to kind of tease that out a little bit more, we're usually working with 16-bit depth files, so we have a wide range of density values, but it's not standardized like it is for medical scanning. So we have to interpret a lot of the density values, but also the anatomy features, so we get really familiar with different weird stuff in cross-section. So our search engine is very different than what it's like for medical scanning in terms of looking for Hounsfield units.
Right, and so no suggestion that spectral imaging is something in the future for those micro CTs?
Not yet, but that is
It's very
something,
cool.
yeah, that would be amazing to try. I'm really interested in that.
Do you guys have a method or a plan to catalog some of your scans so they might be accessible from outside the building? Is there some kind of a system for that?
Yes, thank you for asking. We post most of our scan data on a website called Morphosource, so it's a digital online repository. We are not the only ones that host material there. It's open for any researcher, anybody that's doing scanning, imaging, creating digital models of all kinds of things. And Jurassic Giants has a lot of stuff that's been posted on there. We are posting everything as it gets published. And right now, there are probably 50 or so elements, and then a couple others that are pending publication to be shared. And it's very easy to access. You have to create an account, but you just request whatever it is you want to download. And those files are more often than not like ready to be 3D printed or put into any kind of modeling software that you have.
What invertebrates have you worked on? And when you're not looking for bone, what are you looking for?
Good question. The fossil invertebrates have mostly been like shells. We looked at brachiopods a lot, and for that we were actually looking at muscle scars and the hinge joint of a certain brachiopod called Raphinaskina to see how it was actually opening its valves. That was published earlier this year, if you're interested. It's also available on Morphosource. We've also looked at a wolf spider. It was very awesome. I'm sad that I didn't have time to put it in this presentation, but stay tuned for next time because it's amazing. I've never seen the inside of a spider before. I don't know how many of y'all have ever seen the inside of a spider before, but it's amazing. They have muscles. I didn't know they had muscles. There's just so much anatomy that you can see in this micro CT scan of its head and thorax, and it's really cool. Never thought I would be working on that. The question that we were answering actually wasn't our question. It was a different researcher from the Smithsonian that scanned that, and so we just host the data because it's our specimen. So really cool stuff. Yes, yeah. So look it up, it's awesome. It's a little creepy when you turn it into 3D because it's just a giant spider head looking at you, but it's still pretty cool.
Anyone else? Nobody? All right, thanks for coming, everyone.
Thanks, y'all. There are 3D prints up here if you guys want to come and see some of the stuff that we've worked on and actually touch some fossils.